Alright, this is part 1, the introduction. Hello, my name's Christian. I'm a high school freshman, and this is my talk on complex analysis. Right, first obvious question. What is complex analysis? Well, it's the study of complex valued functions, functions that take in a complex input and produce a complex output. Complex numbers are fascinating because they effectively store two pieces of information in one number. They have a real part and they have an imaginary part. And these two pieces of information are completely separate from each other. So we can do things like plot them on a plane, rather than needing a set of coordinates x and y, like we do for the Cartesian plane. We can just plot a single number in a specific place. And there are some fascinating things you can do with this. This turns out to have applications from pure math in the Riemann zeta function, which applies to distribution of the primes, in nuclear engineering, where it's used in advanced reactor kinetics and plasma physics, and quantum mechanics, where it appears in the Schrodinger equations and wave functions. So, today we're going to be walking through some of the math behind the proofs of two of the most basic theorems and one of the most basic concepts in complex analysis. So, let's get into that. Alright, so here's part 2, terms and notation. Math, of course, uses a lot of symbols and jargon, and it's important that you understand what I mean when I use them. So, first of all, to understand this talk, you're going to need an understanding of the complex numbers, as well as single variable calculus education, roughly equivalent to Calculus 1 and 2 in a standard university curriculum, or AP Calculus BC in the American high school system. There will also be a little bit of multivariable calculus at the beginning, which I will try to explain to you here, and hopefully I do a good enough job of explaining the fundamental ideas behind them that you can understand the math. Right, so let's begin by reviewing the complex numbers. We denote them generally as z, and individual points are denoted with subscripts, such as z sub 0, z sub 1, and so on. These have real and imaginary components, and can be plotted on the complex plane with the real and imaginary axes. Right, so now let's review single variable calculus. You have your single variable derivative, df dx, which is the slope of the tangent line to a single variable function f of x. And then you have your definite integral from a to b of f of x dx, which can be thought of as the area under the curve of f of x from x coordinate a to x coordinate b. So now we generalize this to higher dimensions by starting with our generic two-variable function f of x and y. Two variables because we're working with the two-variable complex plane later on. First of all, we can generalize the idea of the derivative to two dimensions using the partial derivative, which is written del f del x using this reverse 6 looking thing, which is essentially the derivative of this thing, but with y being held constant, so x is the only thing changing. Mathematically, this is the limit as delta x approaches 0 of f of x plus delta x y minus f of x and y over delta x. And you see, this looks like the definition of a single variable derivative, but we have an extra y term in here that we need to keep constant. Then we can generalize the idea of integral using the area integral, or the double integral. We write this using two integral signs and a subscript denoting the region over which we're integrating. And then we have our function, f of x and y, our integrand, and our differentials. And so while this can be thought of as the area under a curve, this can be thought of as the volume under a surface. You don't really need to know how that works for the purpose of this talk, it's just the fundamental idea that's important. This will pop up for a very short time, 2 sections down the road. And then last and possibly most importantly out of all of these is the idea of the contour integral. This is over the imaginary plane exclusively, and it's written using the integral sign, this little circle through it, and then a subscript denoting the contour of f. So this is the integral over the contour c of f of z dz. So what this means is we're taking the integral of this thing over some closed loop in the imaginary plane. And that loop, that contour, that loop, is what c is. This circle here denotes that the contour is closed. That is, the origin point is the same as the end point. But really, you can also integrate over contours that aren't closed. Those are called line integrals. So this is something we'll be seeing pop up a lot more later down the line in this talk. You don't need to know how it works. Again, it involves some fancy parameterization that's beyond the scope of this talk. All you need to know are 2 fundamental things. First of all, integrating in the counterclockwise direction is generally considered positive, while integrating in the clockwise direction is considered negative. You can also add and subtract and break apart you can break apart the integrand in addition and subtraction in the same way you would a normal integral. Right. So then we define 3 terms. We define a function, a complex function f of z, to be complex differentiable at a point z sub 0 if it satisfies the same kind of criteria we have for real differentiability, which is that the limit as z approaches z sub 0 of f of z minus f of z sub 0 over z minus z sub 0, if this limit exists from all directions, we say our function f of z is complex differentiable at that point z sub 0. Next, we say that function is holomorphic if it is complex differentiable over a certain region. So, for example, say f of z is complex differentiable over the region bounded by this contour c. Then we say f of z is holomorphic over that region. And finally, for real or complex functions, we have the term analytic, which means they can be expressed as a convergent power series in the neighborhood of some point. So f of x, let's say it's real, is the infinite sum of some coefficient multiplied by some power of x minus a, which is the distance from x to some center point. Here c sub n is just the nth coefficient of this power series. And you've actually seen these before in the term of Taylor series for, over the real plane in your calculus classes. So, armed with all this, we aim to set out to prove some of the most fundamental results in complex analysis, culminating in a proof that all holomorphic functions are analytic. And all of this will come into play at some point down that line. Next up, we begin by relating complex differentiability to real differentiability a little more closely. All right, so here we have part 3, the Cauchy-Riemann equations. So you'll remember at the end of the last segment, I was talking about how we were looking for a better way to relate complex differentiability to real differentiability. And that's what the Cauchy-Riemann equations give us. So let's derive them. We start by looking at our trusty function f of z. We'll say f of z is holomorphic for the sake of this proof because we kind of need it to be. When it's holomorphic, we can write its general derivative f prime of z which formally is the limit as delta z approaches 0 of f of z plus delta z minus f of z over delta z. And so, it turns out, because you can separate all complex numbers into their real and imaginary parts, we can separate both f and delta z into real and imaginary parts. F of z specifically becomes f of x plus iy. We can use these terms, x and y, as parameters for two variable real and real differentiable functions, u and v, such that u is the real part of f of z, and v is the imaginary part. Then we can separate delta z into real part delta x and imaginary part delta y. Right. And here's the key thing. Because f of z is holomorphic and complex differentiable at every point within the complex plane, it must be complex differentiable from every direction at every point. So we'll take this limit from both the horizontal and vertical directions and compare them. We'll start with the horizontal direction, in which case delta y equals 0, and therefore delta z just equals delta x. This limit can be rewritten as the limit as delta x tends to 0 of f of x plus delta x plus iy minus f of x plus iy over delta x. Separating these f's into u's and v's, this is the limit as x tends to 0 of u of x plus delta x y plus I times v of x plus delta x y minus u of x and y plus I times v of x and y. And hopefully, all over delta x. And you should be able to see how we break these down into these using that. So then, we can break open the parentheses, move the u and v terms together, split the limit, and then factor out the I from the v term to get this whole thing equals the limit as delta x goes to 0 of u of x plus delta x y minus u of x and y over delta x plus I times the limit as delta x goes to 0 of v of x plus delta x y minus v of x and y over delta x. And so, you'll notice that these are what we define as partial derivatives in the previous section. Specifically, this is del u del x, and this is del v del x. That's a really bad v. So, because we said this was f prime of z, we have that f prime of z, the horizontal direction, is equal to del u del x plus I times del v del x. So now let's try it from the vertical direction and see if we get something different. Okay, so from the vertical direction, delta x equals 0, and therefore delta z is just I delta y. Once again, we write the limit as I delta y tends to 0, which is just as delta y tends to 0, of f of x plus iy plus I delta y minus f of x plus iy over I delta y. Again, we split f into u and v, such that this is the limit as delta y tends to 0 of u of x and y plus delta y plus I times v of x, y plus delta y minus u of x and y plus I times v of x and y, all over I delta y. Once again, we break open the parentheses, combine the u's and v's, break the limit, all that, and eventually we get that the limit as delta y approaches 0 of u of x, y plus delta y minus u of x and y over I delta y plus the limit as delta y approaches 0 of v of x, y plus delta y minus minus v of x and y over delta y. These two are the same. There's no I in the denominator here because the I from the numerator cancels. So then we can move this I outside, 1 over I. I to the negative 1 is the same thing as negative I. And again, we have two partial derivatives here. This is del u del y, and this is del v del y. So once again, we have another way to write f prime of z, such that it is equal to del v del y minus I del u del y. So, we have two different ways to write the exact same thing. So these two are equal. More specifically, their real parts must equal, and their imaginary parts must equal. And so, we get del u del x equals del v del y, and del v del x equals negative del u del y. And these are known as the Cauchy-Riemann equations, and these are the basic criteria for complex differentiability. If f of z is complex differentiable at a point, then these equations must be satisfied at that point. And it goes vice versa. If these equations are satisfied at that point, f of z is complex differentiable at that point. So let's do an example. Let's take the simple complex function f of z equals z squared. This is x plus iy squared, which equals x squared minus y squared plus 2ixy. We separate this into real and imaginary parts such that u of x and y equals x squared minus y squared, and v of x and y equals 2xy. So then, let's take each partial derivative. The partial derivative of u with respect to x holds y constant, and so that term is just dropped. It's clear to see that del u del x is just 2x by the power rule. Now del v del y, down here, x is kept constant, y is taken derivative of, the derivative of the first degree is just 1, so this is 2x, and you see these are equal. This is satisfied. Now, del v del x, same thing, except now the other way around, so this is 2y, and then del u del y holds x squared constant, and so again, power rule, this is negative 2y, and you see, this is the negative of that, and this is satisfied. So, next time, we'll be using this set of equations to generalize real multivariable calculus into the complex plane and beyond. Alright, here's part 4, deriving Cauchy's integral theorem. So to recap last time, we found a formula or a set of equations that allowed us to relate real differentiability to complex differentiability, the Cauchy-Riemann equations, which I'll rewrite up here. Del u del x equals del v del y, and del u del y equals negative del v del x. We had it backwards last time. Right. So, this is where the multivariable starts. So bear with me here. We will begin with what is sometimes referred to as the fundamental theorem of multivariable calculus, and you'll see why in a moment. The generalized Stokes theorem. It states that the integral over the boundary of a region big omega of some differential form small omega equals the exterior derivative of that differential form over the entire region big omega. Now what the hell does that mean? You don't really need to know what it means mathematically, but essentially what it's doing is it's relating an integral over a boundary of some region to an integral over that region itself. And in fact, your fundamental theorem of single variable calculus, the integral from a to b of f of x dx, is equal to its antiderivative the differences of its antiderivative at the endpoints, this is actually just a special case of that when the contour is a line segment. But the complex plane is two-dimensional, and so we need a two-dimensional special case for this. And that is conveniently provided by Green's theorem, which states that the contour integral of L dx plus m dy for two variable functions L and m, this is equal to the area integral over the region bounded by C, which is D, of del m del x minus del L del y dx dy. And this is where our area integral comes in. Right. So a lot of this looks kind of familiar to what we saw last time with deriving the Cauchy-Riemann equations. We have two variable functions, we have partial derivatives, and so on. So let's see if we can relate them somehow. We go back to f of z, and we split it up into u plus iv. We'll skip the x and y for now. So let's try taking the integral over c of this. With respect to the derivative of z, we can also break the differential dz into dx plus I dy. And so this becomes the integral over c of u plus iv dx plus I dy. And then distributing this, we get that this equals the integral over c of u dx plus iv dx plus u dy minus v dy. And we can move these terms around and separate it by addition, such that this integral is equal to the integral over c of u dx minus v dy plus the integral over c of, well, I times that, because it's independent of the variables of integration, of v dx plus u dy. And now we have two things that look like the left side of Green's theorem. So, I should have enough space here. Then, we can replace both of these with area integrals by Green's theorem. So let's take this up to the top over here, and this equals the area integral over d of m here is v, m here is v, and L here is u. So this is del v, negative del v del x minus del u del y dx dy plus the area integral over d of, here, u is m and v is L, so del u del x minus del v del y dx dy. Right. So now we have a bunch of partial derivatives. And you know where we just saw partial derivatives? That's right, the Cauchy-Riemann equations over there. So we can plug in one of these for one of those, and over here, for example, negative del u del y, well, del u del y equals negative del v del x, so this equals positive del v del x. And then over here, del v del y equals del u del x. So we have u del x. And you can see the integrands cancel out to 0. So really what this is the area integral over d, 0 dx dy, plus the area integral over d of 0 dx dy. And because the integrands are 0, the integrals are 0. And so this comes out to 0. And remember again that this was the integral over c of f of z dz. So we get this interesting result, that the integral over a closed loop C of f of z dz equals 0, provided that f of z is holomorphic over the region bounded by C. And this is one of the most fundamental results in the field of complex analysis. Next time, we'll take this to derive a more useful formula for determining the value of the integral of the function at a certain point. That's known as Cauchy's integral formula, and we'll be looking at that next. Alright, here's part 5, Cauchy's integral formula. So to recap our previous section, we proved Cauchy's integral theorem, stating that for a holomorphic function f of z over a region bounded by some contour C, the integral over C of f of z dz is just 0. So we can see this on the complex plane with our real and imaginary axes as that for some contour, any contour, as long as it doesn't enclose a singularity, and f of z is holomorphic over the entire thing, the integral of any holomorphic function f of z over this contour is 0. So, what if we now want a better formula? Something that will give us more information than just something equals 0. What if we want a way to evaluate f of z at certain points within this contour? And that is what Cauchy's integral formula gives us. Here I think it's easier to state the formula and then explain the derivation. So we'll do that. Cauchy's integral formula states that f of z sub 0 for some point z sub 0 within our contour C, f of z sub 0 equals 1 over 2 pi I times the integral over the contour C of f of z over z minus z sub 0 dz. Essentially, what this means is you can find the value of our complex function f at any point within a contour C as long as f of z is holomorphic over that contour and you know some of the values along that contour. You know what this integral evaluates to. So, the first thing you're probably asking is, well, why doesn't this just evaluate to 0? This bit. F of c is holomorphic. You have the integral over c with respect to z. So, why doesn't this just evaluate to 0 like Cauchy's integral theorem? Well, because this isn't exactly f of z. It contains this little z minus z sub 0 at the bottom, and that's what makes all the difference. Because that means this function, f of z over z minus z sub 0, is actually undefined at the point z sub 0 within C. And so, f of z over z minus z sub 0 is not actually holomorphic over all of C. It's holomorphic over all of C except for this one point, z sub 0. And this one annoying point is enough to fail the preconditions to use Cauchy's integral theorem. So, let's go on with the proof. For simplicity's sake, we'll use circles to represent our contours here, because they're the same thing. The contours can be deformed as long as they don't pass over a singularity. So, we have our contour C, or circle, and within C, we have the point in question, C sub 0. Now, we don't know how to evaluate this just yet, because we have this pesky point z sub 0 in the middle of it. So wouldn't it be nice if we could just separate that out? Well, what we can do is we can draw a smaller circle, an arbitrarily smaller circle, within C that encloses this point z sub 0. And now you can see that this area that's within C and outside the smaller circle gamma, f of z over z minus z sub 0 is holomorphic within this region because it doesn't contain z sub 0. So, how do we make this into a contour? Well, we can split it up into two contours. We take the contour over the top half, or at least the upper section, of C and gamma, and we call this contour C plus. We then do the same for the bottom half, the bottom section, and we call this contour C minus. And once again, all of these are measured in the counterclockwise direction, the counterclockwise direction being positive by convention. So, we have these two contours now, and neither of these contain our original point z sub 0. So, the integral over both of these contours of f of z over z minus z sub 0 dz is 0 by Cauchy's integral formula. Integral theorem, sorry. And same for z minus. So, how do we get this back in terms of c and gamma? Well, looking at this, you'll note that both of these are, of course, traversed counterclockwise. So, when you combine these two contours, they enclose the entirety of C one time, the entirety of gamma one time, and then you have these two little lines sticking out in the middle. Conveniently, because these lines are traversed in opposite directions, the integrals over these lines cancel each other out. It's like you walk forward a step, and then you walk backwards a step. You're back where you started. The integrals over these lines are 0. So then we're left with the integral over C in a counterclockwise direction, which by convention is positive, again, and then the integral over gamma in a counterclockwise direction, which is negative by convention. So you have that the sum of these two things, the sum of the integral over C plus of f of z over z minus z sub 0 dz, plus the integral over C minus of f of z over z minus z sub 0 dz equals the integral over C of f of z over z minus z sub 0 dz minus the integral over a smaller circle gamma of the same thing. And we just showed that this bit is equal to 0. So, some simple arithmetic, moving this to that side, tells us that the integral over gamma of f of z over z minus z sub 0 dz is equal to the integral over c of f of z over z minus z sub 0 dz. Now, we have this bit, which corresponds to this bit in Cauchy's integral formula. So where do we get the f of z sub 0 and the 1 over 2 pi I from the other side? Well, let's do a little work on that side. So we take our integral over gamma of f of z over z minus z sub 0 dz. Well, first of all, we can get our f of z sub 0 term in there by just adding and then subtracting it from the numerator. Plus f of z sub 0 minus f of z sub 0 dz. Still all over z minus z sub 0. Obviously, these two cancel out, and it's the exact same thing. But now, we can separate this fraction, and this is the integral over gamma of f of z sub 0 over z minus z sub 0 plus f of z minus f of z sub 0 over z minus z sub 0 z. And then, using our regular integral rules, we can separate this out by addition. So this is the integral over gamma of this dz plus the integral over gamma of this dz. And then because f of z sub 0 is independent of the variable of integration here, we can separate this out. 1 f of z sub 0 times that. I'm running out of room a little bit there, but you should be able to see that. So we have our f of z sub 0 term here, and then we have to figure out what to do with all this. We'll look at these two individually. It can be seen that this one actually just evaluates to 2 pi I by some simple parameterization into the reals. That's a little bit on the scope of this talk, but the essence of it is you can rewrite this integral using the unit circle as the contour, as the integral over 0 to 2 pi of I times e to the it over e to the it dt, which is just the integral from 0 to 2 pi of I dt, which is 2 pi I. So this turns out to be 2 pi I. This turns out to actually have Cauchy's integral theorem be applicable to it, despite not being complex differentiable at that point, by a little extension of Cauchy's integral theorem that, for the sake of time, I'm not going to go too deep into. But, essentially, this bit also evaluates to 0. So then, you get that the integral over c of f of z over z minus z sub 0 dz equals 2 pi I times f of z sub 0. Dividing both sides by 2 pi I, we get our original intended result. 1 over 2 pi I times this equals f of z sub 0. And that is exactly what we see up here. So, we've now derived a method to determine the value of a complex function at any point, so long as we know that there is a contour surrounding that point over which f of z is holomorphic, and we know what the contour integral of that thing is. So next time, we'll be using this to prove our final result of today's talk, which is that complex holomorphic functions are analytic, meaning they can be expressed as a convergent power series. And this has major effects throughout the field of complex analysis. So stay tuned for that. Alright, here's part 6, the proof of analyticity. So last time, we proved Cauchy's integral formula, a formula that allows us to evaluate our complex holomorphic function f at a point z sub 0. Specifically, it is equal to 1 over 2 pi I times the contour integral over a contour c of f of z over z minus z sub 0 dz. Geometrically, on the complex plane, we have our contour c, which we used a circle for to simplify calculations. Not the best circle, but you get the idea. Contour c, and then we have our point z sub 0 within that. Right. So now we want to prove, using this, that any holomorphic function f can be written as a convergent power series around a point A. That is, it can be expressed as the infinite sum from 0 to infinity of a series of coefficients, c sub n, times z minus a at the n, where a is the center of the radius of convergence of this power series. So, how do we get from here to something that looks remotely like that? Well, first, let's rewrite what's inside this integral. So we have 1 over 2 pi I times the integral over c of f of z over z minus a times 1 minus z sub 0 minus a over z minus a, where a here is the center of our circle contour C. Now, we can separate this by a multiplication into two fractions, and you'll notice, sorry I forgot the dz, you'll notice that this bit over here looks like our formula for the sum of an infinite geometric sequence, a sub 0 over 1 minus r. So we can rewrite this as the sum from 0 to infinity of z minus a, z sub 0 minus a over z minus a to the n. And because this is a constant, we can move that inside as well. So this becomes the integral over c of the infinite sum from 0 to infinity of f of z over z minus a times z minus a over z sub 0 minus a over z minus a to the n. So we know for a fact that this has to be convergent because the absolute value of z sub 0 minus a over z minus a has to be less than 1. And for a quick refresher, the absolute value of a complex number is its distance to the origin. So essentially, z sub 0 minus a has to be less than z minus a because z is somewhere on the contour C, while z sub 0 is any point inside C. Because we have C as a circle, the distance between any point z and a is just r, the radius of C. And then z sub 0 minus a will always be less than that because it's within C. So this is less than 1, and this geometric sequence converges. So if we were just able to swap this sum and integral, we would be able to rewrite f of z sub 0 in this form. So how do we do that? First, we need to prove that this infinite sum converges absolutely and uniformly over this region. So what we'll use for that is a convergence test called the Weierstrass M-test. You may or may not have learned this in your Calc 2 course, but essentially what this says is that for a series of functions, f sub n of z in this case, if you can prove that all of them are bounded by some value n, m, and the infinite sum of m's converges, then the infinite sum of f's converges. Which kind of makes sense when you think about it, right? If you can prove that the infinite sum of something bigger converges, surely the infinite sum of something smaller should also converge, right? So we can break this up into individual pieces. We have f of z times 1 over z minus a times z sub 0 minus a over z minus a to the n. Because f of z is continuous and holomorphic over this whole area, it has to be bounded by some maximum value. It can't just go off to infinity. So we'll call this value, even though it's a little confusing, m. So f of z has to be less than some finite value m. 1 over z minus a is simply 1 over the radius of this contour C, which, very visibly, is finite. So this has to be less, well, this is equal to, strictly, 1 over r. And then here, because we just proved that this, what's inside here, the ratio, has to be less than 1, this is bounded by some value n that is greater than or equal to 0, but less than 1. So, what's inside this series, the infinite sum of f of z over z minus a times z sub 0 minus a over z minus a to the n has to be less than or potentially equal to 1 over the infinite sum of m over r times n to the n. And because we have n between 0 and 1, this converges, and therefore this converges absolutely and uniformly, what's inside here. And that is enough to allow us to swap this sum and integral up here. So this is really 1 over 2 pi I times the infinite sum of the integral of this over c. Then, because that's constant, we can work that inside. And because z sub 0 minus a is independent of the variable of integration here, and it's constant over here, we can actually just factor that out of this z minus a to the n over here, and then move it all the way out here, just outside of the infinite sum, z minus a to the n. And now we have our z minus a to the n, and then we have some coefficient. So if we write c sub n, let me get a different color, c sub n equals 1 over 2 pi I times the integral over c of f of z over z minus a to the n plus 1, z minus a times z minus a to the n dz. Then we have that this equals the infinite sum of c sub n times z minus a to the n, which is exactly what we were looking for. So there you have it. Any holomorphic function, f of z, is necessarily analytic. It can be expressed as the infinite sum of a convergent power series. And next time, we're going to look at a few consequences of what we've looked through and wrap up this talk. So stick around just a little longer. All right, and here's part 7, the conclusion. So today we've walked through the basics of complex analysis, from the Cauchy-Riemann equations to deriving Cauchy's integral theorem, then Cauchy's integral formula, and finally proving that holomorphic functions are analytic. So here are some of the corollaries of that theorem, of that idea. So, first of all, the radius of convergence of our power series expansion that we showed last time is necessarily the distance from our center point to the nearest singularity. And this seems kind of intuitive, because remember when we proved the whole analytic thing in the last section, we used an open ball, a circle, centered at some point A. And so let's say we have some singularities scattered throughout the complex plane at these black points. The greatest radius of an open ball we can make over which f of z is holomorphic is necessarily the distance to the closest one of these singularities. That is a really bad circle. But you get the idea. Because if the radius of this circle was any larger, that singularity would be enclosed in it. At that singularity, the function is not well behaved, and so f of z would not be holomorphic over that area. So the radius of convergence for our power series expansion centered at this point A is just the distance from A to the nearest singularity. Next, from that, what we proved last time, we can derive the identity theorem, and from that, say that complex functions are what we call rigid. That is, if you know the values on just a small subset of the complex plane, this area over here, say, you can then derive the values of that function for the rest of the complex plane over which it is defined. Or, well, over which it's not defined, perhaps, because that's kind of the point of this process, which is known as analytic continuation. And this rigidity of complex functions is in contrast to the, perhaps, softness of real functions, where its values on one part of the plane have nothing to do with its values on another part of the plane. However, in the complex plane, you can't change the function here without changing it there, and vice versa, and so on. And the final thing is that from Cauchy's integral formula, we can also derive a formula for differentiation, because with our power series expansion, we know power series are infinitely differentiable, and therefore holomorphic functions are infinitely differentiable as well. Specifically, the nth derivative of f of z is equal to n factorial over 2 pi I times the integral over c of f of z over z minus z sub 0 to the n plus 1 dz. And this does look kind of like Cauchy's integral formula, hence why it's, derived from there. But this is a formula that will allow us to get the nth derivative of f of z. Right. So, these three things that we derived today, Cauchy's integral theorem, Cauchy's integral formula, and our proof that holomorphic functions are analytic, form most of the baseline of complex analysis, along with another fundamental result derived from Cauchy's integral formula called the residue theorem that I've decided to leave out of this talk for the sake of time. Anyway, that's about it for this. I did not do the best job of explaining all this, but there are resources online like Wikipedia and other math resources that you can look to if you need some clarification, and there's always the comment section or ChatGPT. Thank you for watching.